What is the most successful physics theory ever? Well, after looking into it for not too long, I found this. Hailed by many since then as the most successful theory ever conceived, the Standard Model describes the universe with a comprehensiveness that is hard to understate. All the particles it predicted to exist have been found, meaning it has an accuracy of 100%. So technically, by extension, it is the most successful theory ever. But what the hell actually is the Standard Model? Well, I looked into it, and here's what I found. On October 17th, 1967, physicist Steven Weinberg published a paper called A Model of Leptons. It was revolutionary, and it was only 3 pages long, but he did win the Nobel Prize in Physics for this, and subsequently 56 other physicists also won a Nobel Prize for their research into the Standard Model. It says that every particle is either a fermion, which is a matter particle, or a boson, which is a particle that regulates the forces of nature. Fermions. So there are 4 types of fermions. Electrons. They generate an electric field that exerts an attractive force on a particle with a positive charge, such as a proton, and a repulsive force on a particle with a negative charge, such as the electron itself. Neutrinos. Unlike electrons, they are not electrically charged, they are electrically neutral. These two are the so-called leptons, described in Weinberg's paper. And then there are quarks, more specifically up and down quarks. Quarks form together to form protons and neutrons. Those then combine into a nucleus, and together with electrons, you have an atom. Each of these particles has 3 generations. The up quark, the charm quark, and the top quark. The down quark, the strange quark, and the bottom quark. And then the electron, the muon, and the tau. And well, the neutrinos are just very inventively named after the electron. We can create these further generations of particles, but they quickly decay back into the first. This is due to one of the fundamental forces. That's where the bosons come in. Bosons are responsible for the fundamental forces of nature. The most famous boson, the photon, responsible for electromagnetism. The force that glues quarks together, called the strong force, is attributed to the boson, which was first theorized by and then inventively named gluon by this guy right here. If there is a strong force, you might think there would be a weak force, and that does exist. The first theory of the weak force was published in 1933 by Enrico Fermi, the same guy fermions are named after. Via charged particles, the weak force can change the orientation of quarks from up to down and down to up, changing protons into neutrons and neutrons into protons. The boson, or rather bosons, that mediate this force are called the W and Z bosons. Particles more massive than entire iron atoms. Now, if you're into science, you're probably thinking, wait, if the bosons are supposed to be responsible for the different forces of nature, what the hell is up with gravity? And you're justified in thinking it. Gravity is not included in the Standard Model, showing that it is still incomplete. There is the graviton, a theoretical particle responsible for gravity. But this does not play nice with Einstein's theory of relativity. So the problem of quantum gravity is still an unsolved mystery. And I'm probably going to look into this further, and I might make a video on it, because it is interesting. But this is the fundamental issue we're trying to solve. How do quantum and classical physics interact? That's one of the big roadblocks on a long road to a potential theory of everything, which is a goal humanity might never achieve. Now, you know how I said earlier that the Standard Model has an accuracy of 100%. Well, after trillions of collisions and years of data collection and number crunching, the CDF team have found that the W boson has slightly more mass than expected. After 11 years of data analysis, the CDF team at Fermilab have managed to significantly decrease the overall error in measuring the mass of the W bosons, from the next best plus minus 19 to just plus minus 9. what they found is that the mass of the W boson is 0.1% higher than what is predicted by the standard model. And on the scale of particles, that is significant. There are two options. Either our results are wrong, or a standard model, or at least some part of the standard model, is wrong. And that's a very scary idea. But it's also what makes this so exciting, because in the end, that is what we want. That is the scientific method, to prove or disprove all theories, and with the new information that we have, refine those old theories or make completely new ones. The bosons I've talked about so far are gauge or vector bosons, but there is one central piece of the standard model missing: the Higgs boson, a scalar boson supposed to give mass. And that's what I'm going to be looking into further for next video.